Pick up a glass of water, any glass. Look at it. That water is not from Earth. By every law of physics, Earth should be as dry as Mercury. When our planet was forming 4.5 billion years ago, the temperature at its surface was high enough to vaporize any water into space, permanently. And yet, oceans exist. Rivers run. You are 70% water, which means it came from somewhere else. But from exactly where? That is one of the most fiercely contested questions in modern science. Because every time scientists think they have found the answer, new data turns everything upside down. This is the story of the greatest detective investigation in the history of this planet. And the clues are scattered across the entire solar system. If you are interested in how science solves mysteries that seem impossible, please subscribe to this channel. Your support genuinely helps us keep making this work. Thank you. The Earth, when it formed 4.5 billion years ago, was a roasting, airless rock sitting dangerously close to a violent young star. Water, delicate, lightweight, volatile, had no business being here. The sun's radiation should have blasted every last molecule into space before it could settle. And yet, 1,380,000,000 cubic kilometers of ocean exist on this planet today. Rivers run. Ice caps sit at the poles. Your body is 70% water. So where did it come from? That question sounds simple. It is not. It has consumed some of the finest scientific minds of the last half-century. It has sent spacecraft on 10-year journeys to the edges of the solar system. It has cracked open meteorites that fell from the sky and found, inside them, water older than the Earth itself. And every time science thought it had the answer, something new arrived to complicate the picture. This is not a story about water. This is a story about how a planet got lucky. About the invisible chain of events, collisions, migrations, gravitational accidents that had to go exactly right for any of us to be here at all. Change one link in that chain, and this planet looks like Mars, bone dry, silent, dead. We are going to follow that chain back to the very beginning, and by the end, that glass of water in your hand is going to feel like something close to a miracle. September 28th, 1969. A Sunday morning in Murchison, Australia. Population 800 people. Most of them are heading to church. At 10:58 in the morning, the sky tears open. A fireball the size of several city blocks screams across the atmosphere from northwest to southeast. The sound, a rolling, bone-deep concussion, is heard 500 kilometers away. Fragments begin raining down on the town. One punches through the roof of a barn, another lands in the middle of a road. Local farmers run outside and find dark, fist-sized stones with a strange, glassy crust, as if they had been partially melted and then flash frozen. And then there is the smell. One farmer, Arthur Brady, picks up a fragment and later describes the odour as something like methylated spirits. Organic. Chemical. Wrong, somehow, for a rock. Within days, scientists from across Australia are descending on Murchison. The stones are collected, catalogued, and shipped to laboratories. And what those laboratories find over the following years will permanently change the way we understand where Earth's water came from. But to understand why that meteorite mattered so much, we first need to understand the problem it was helping to solve. And that problem begins not on Earth, but in the catastrophic early life of the solar system itself. Imagine the Sun at roughly 2 million years old. That is an infant by stellar standards, a furious, unstable infant. Around it spins an enormous flat disk of gas and dust, the raw material from which all the planets would eventually form. The inner part of that disk, close to the young star, is brutally hot. Temperatures near what will become Earth's orbit reach several thousand degrees Celsius. At those temperatures, volatile compounds, water, carbon dioxide, ammonia, cannot exist as solids. They are vaporized instantly and pushed outward by the relentless pressure of what scientists call the T-Tauri wind. The T-Tauri wind is what very young stars do before they settle down. They blast their surroundings with a torrent of charged particles hundreds of times more intense than the solar wind we experience today. This wind acts like a colossal leaf blower aimed at the inner solar system, stripping away anything light enough to be carried off. Water is light enough. The boundary where temperatures drop enough for water ice to survive as a solid is called the snow line. In our early solar system, that line sat at roughly 2.5 astronomical units from the Sun, just beyond where Mars would eventually form, right at the inner edge of what we now call the asteroid belt. Inside that line, the region where Earth was assembling itself from colliding rocks and dust, water simply could not persist. The math is brutally clear. The temperature at Earth's surface during the magmatic ocean phase, the period when the entire planet was essentially a globe of molten rock, exceeded 1,200 degrees Celsius. Water boils at 100 degrees. At 1,200, it does not merely boil, the molecule itself tears apart. Hydrogen escapes to space. Oxygen bonds with iron and silicates in the rock. And if you need a real-world comparison for what happens to a rocky inner planet that cannot hold onto its water, look at Mars. Mars sits farther from the Sun than Earth. It is colder. It formed closer to the snow line. By every reasonable expectation, it should have more water than Earth, not less. And 4 billion years ago, it did. The evidence is written into its geology. Ancient river channels carved into the southern highlands, enormous dried lake beds in the Hellas Basin, minerals that only form in the presence of liquid water. Mars once had oceans. Maybe shallow, maybe brief, but real. Then it lost them. Its smaller mass meant weaker gravity. Weaker gravity meant a thinner atmosphere. A thinner atmosphere meant less protection from solar radiation. The water evaporated, the hydrogen leaked to space, and Mars dried out over roughly the first billion years of its existence. Earth faced the same conditions. Earth survived them. The question is why? Scientists have been interrogating that question for decades, and the primary tool they use is one of the most elegant in all of chemistry. It is called isotope analysis, And once you understand it, you will see why it transformed this investigation from a guessing game into something approaching a proper detective story. Hydrogen, the H in H2O, is not a single thing. It exists in nature in two stable forms. Regular hydrogen has a nucleus containing just one proton. But there is a heavier version called deuterium, whose nucleus contains one proton and one neutron. That extra neutron makes deuterium roughly twice as heavy as ordinary hydrogen. When deuterium bonds with oxygen to form water, you get what chemists call heavy water, chemically identical to regular water, but measurably denser. The ratio of deuterium to ordinary hydrogen in any sample of water, the D to H ratio as scientists write it, acts like a chemical fingerprint. Water that formed in the cold, radiation-rich environment of interstellar space tends to be rich in deuterium. Water that formed closer to a warm star tends to be depleted in it. The specific D to H ratio of Earth's oceans is a fixed, well-measured number. Approximately 1 deuterium atom for every 5,100 ordinary hydrogen atoms. If we can find a source, an asteroid, a comet, a cloud of interstellar gas, whose water carries that same ratio, we have found the origin of our oceans. The hunt was on, and the first major clue came from inside that meteorite that fell on Murchison, Australia in 1969. The Murchison meteorite belongs to a class called carbonaceous chondrites, specifically the CM2 subtype. These are among the most ancient objects in the solar system, formed 4,500,000,000 years ago, before the Earth itself existed. They are essentially preserved samples of the raw material the solar system was built from. And when scientists cracked them open and analysed their mineral structure, they found something astonishing. Water. Not traces, not hints, real, chemically bound water, locked into the crystal lattice of hydrated silicate minerals. The kind of water that does not evaporate under normal conditions because it is not sitting in a puddle. It is woven into the structure of the rock itself. The Murchison meteorite contained roughly 12% water by mass, and the D to H ratio of that water was strikingly close to the ratio found in Earth's oceans. Not identical, close. Tantalizingly, frustratingly close. By the 1990s, a growing body of analysis on carbonaceous chondrites of various types, CI chondrites, CM chondrites, CR chondrites, showed that their water consistently fell in a range that bracketed Earth's oceanic value. The chemical fingerprint was beginning to match. But there was an obvious objection. Yes, these meteorites contain water. Yes, the isotope ratio is similar to Earth's. But the meteorites falling on Earth today are remnants, fragments. The question is not whether individual rocks contain water. The question is whether enough of them fell on the early Earth in sufficient quantity to account for 1,380,000,000 cubic kilometers of ocean. That is an almost incomprehensible volume. To give you a sense of scale, if you could somehow drain all of Earth's oceans and fill them back up using a fire hose flowing at 1 cubic kilometer per second, and no fire hose in history has ever come close to that, it would still take you 43,000 years to finish the job. Where did all of it come from? The answer arrived not from a laboratory, but from the craters on the Moon. When the Apollo missions returned lunar samples in the late 1960s and early 1970s, geologists noticed something peculiar about the Moon's surface. The crater density was not uniform. Some regions were ancient and saturated, so many craters overlapping that counting them individually became impossible. Other regions were relatively smooth and geologically recent. When scientists used radioisotope dating to establish the ages of rocks from the heavily cratered zones, a pattern emerged that nobody had anticipated. The overwhelming majority of the Moon's largest impact craters formed within a very narrow window of time, approximately 4 billion years ago, give or take perhaps 100 million years. This concentrated period of bombardment was given a name, the Late Heavy Bombardment. And it was not limited to the Moon. The same signature appears in the geological record of Mars, of Mercury, and, though the evidence is more difficult to preserve on an active, tectonically dynamic world, almost certainly of Earth as well. Something disturbed the solar system approximately 4 billion years ago and sent a storm of asteroids raining down on the inner planets. The intensity of that storm, by modern estimates, was extraordinary. The total mass of material that struck Earth during the late heavy bombardment may have been somewhere between 10 and 20 quintillion kilograms. Numbers so large they resist intuition. If a meaningful fraction of those impactors were carbonaceous chondrites, water-rich rocks from the outer asteroid belt, the math starts to work. The water budget starts to balance. But this raised an immediate and deeply inconvenient question. What sent them there? What disturbed the asteroid belt so dramatically 4 billion years ago after hundreds of millions of years of relative calm? The answer to that question involves the largest planet in the solar system. And when you understand what Jupiter did to the early solar system, the story of Earth's water becomes something stranger and more extraordinary than anyone had imagined. In 2005, a team of planetary scientists working at the Observatoire de la Côte d'Azur in Nice, France, published a paper that would become one of the most influential works in planetary science of the last 20 years. The lead author was Alessandro Morbidelli. The model they described has been known ever since as the Nice model, named for the city where it was developed. The Nice model addressed a deceptively simple question. Why do the giant planets of the outer solar system, Jupiter, Saturn, Uranus, Neptune, occupy the orbits they do today? The answer, Morbidelli's team argued, is that they did not always occupy those orbits. They migrated. In the early solar system, the 4 gas giants were packed together in a much more compact configuration, somewhere between roughly 5 and 15 astronomical units from the Sun. Beyond them stretched an enormous disk of small bodies, the raw material that would eventually become the Kuiper Belt. For several 100 million years, the system was relatively stable. Then, something changed. Through a process of gradual gravitational interaction, angular momentum exchanged between the giant planets and the small bodies of the outer disk, Jupiter and Saturn drifted into what is called a mean motion resonance. Their orbital periods synchronized in a precise mathematical ratio of 1 to 2. Jupiter completed exactly 2 orbits for every single orbit Saturn completed. That resonance acted like a tuning fork struck at exactly the wrong frequency. It destabilized the entire outer system. Uranus and Neptune were flung onto new, wider orbits, plowing through the outer disk of small bodies like bowling balls thrown into a crowd. Thousands of those objects were scattered inward, toward the Sun, toward the inner planets, toward Earth. That was the late heavy bombardment. But Morbidelli's team went further. In 2011, they published an extension of the NICE model known as the Grand Tack hypothesis. And this is where the story of Earth's water gets genuinely extraordinary. The Grand Tack proposes that Jupiter did not always sit at 5 astronomical units from the Sun. In the first few million years of the solar system's existence, before the planets were even fully formed, Jupiter migrated inward, dramatically. It travelled from its birthplace near 5 astronomical units, all the way down to roughly 1.5 astronomical units, almost to where Mars sits today. It came perilously close to the inner solar system, and then it stopped and turned around. The reversal was caused by Saturn. As Jupiter moved inward, Saturn, still forming in the outer disk, was pulled into gravitational resonance with Jupiter, and the combined interaction dragged Jupiter back outward to something close to its current position. The technical term for this gravitational about-face is a tack, borrowed from sailing, where a tack is the maneuver of turning a sailboat into the wind, hence the Grand Tack. The consequences of this migration were enormous. As Jupiter swept inward through the region between roughly 3 and 5 astronomical units, the zone just outside the snowline, it acted like a gravitational plough. It scattered the rocky, water-poor bodies of that region inward, and it swept the water-rich bodies from farther out, the carbonaceous asteroids that had formed beyond the snowline, and deposited many of them into what would become the main asteroid belt. In other words, Jupiter physically transported water-rich material from the cold outer solar system and parked it in a region from which it could eventually rain down on the inner planets. Without Jupiter's migration, the asteroid belt would contain far fewer carbonaceous chondrites. The late heavy bombardment, when it came, would have delivered far less water to Earth. Current simulations suggest that removing Jupiter's influence from the calculation reduces Earth's water delivery by at least an order of magnitude. An order of magnitude. 10 times less water. Perhaps no ocean at all. Jupiter did not just protect Earth from asteroid impacts, which is the role it is usually given in popular accounts of solar system history. Jupiter delivered the water. Jupiter is the reason this planet is blue. Now, the NICE model and the Grand Tack are not without their critics. Science rarely produces unanimous verdicts, and planetary formation models are constrained by limited data stretched across timescales that no human instrument has directly observed. Some researchers argue the Grand Tack's inward migration was less extreme than Morbidelli proposes. Others have suggested alternative mechanisms for delivering water-rich asteroids to the inner solar system. But a remarkable piece of evidence arrived in 2023 that lent powerful support to the asteroid hypothesis, and to the specific isotopic argument that had been building for decades. The spacecraft was called Hayabusa 2. It was built by the Japan Aerospace Exploration Agency. It launched in December 2014, travelled 300 million kilometres to a small, dark, roughly diamond-shaped asteroid called Ryugu, collected samples from its surface, and returned those samples to Earth in December 2020. Ryugu is a C-type asteroid. a carbonaceous body, chemically related to the carbonaceous chondrites that had been identified as prime suspects in the water delivery story. When scientists opened the sample capsule and began analyzing the material inside, the isotopic data was extraordinary. The D to H ratio of water extracted from Ryugu samples was 1 to 157 micromolar. Earth's oceanic value is 1 to 156. 1 unit of difference, within the margin of measurement error. That is not a close match, that is a match. A direct, unambiguous chemical link between a carbonaceous asteroid and the water in Earth's oceans. The fingerprint on the weapon had been confirmed. But here is where the story takes a turn that almost nobody saw coming. Because in 2021, a team at the University of Glasgow published a paper in Nature Astronomy that proposed a third source of water that had been sitting, quite literally, in plain sight for the entire history of the solar system. Professor Luke Daly and his colleagues were studying microscopic dust grains collected from the surface of the asteroid Itokawa by the original Hayabusa mission in 2010. They used a technique called atom probe tomography, an instrument so precise it can analyze the composition of matter one atom at a time to examine the outermost surface of those grains. What they found, in the first few nanometers of depth, a layer thinner than a soap bubble, was water. Not ancient primordial water locked into mineral structure, freshly synthesized water, created by the solar wind. The mechanism is elegant. The solar wind is a constant stream of charged particles flowing outward from the sun. The vast majority of those particles are protons, bare hydrogen nuclei, traveling at hundreds of kilometers per second. When those protons strike the surface of a silicate mineral, which is rich in oxygen, they embed themselves in the crystal lattice. Hydrogen plus oxygen equals water. The reaction happens atom by atom, nanometer by nanometer, over millions of years of continuous solar bombardment. The water produced by this process has a very different isotopic signature from the water in carbonaceous chondrites. It is almost completely free of deuterium. Its D to H ratio is extremely low, much lower than Earth's oceanic value. And this is precisely where the two sources fit together like puzzle pieces. Carbonaceous chondrite water is slightly too heavy in deuterium relative to Earth's oceans. Solar wind synthesized water is far too light. Mix them in the right proportion, and the result is Earth's oceanic value. Two sources, one too rich in heavy hydrogen, one virtually free of it. Combined, exactly what we find in every ocean, river, and raindrop on this planet. The implication is startling. A portion of Earth's water, the analysis suggests it could be up to a few % of the total, though estimates vary, was not delivered from space at all. It was manufactured molecule by molecule on the surfaces of dust grains that were already part of the planet's building material, cooked into existence by the same star that the planet formed around. The sun, in a sense, helped water its own planet. But we are still missing one piece of the timeline. Because all of this, the asteroid delivery, the Jupiter migration, the solar wind synthesis tells us where the water came from. It does not quite tell us when the first ocean formed. And the answer to that question turned out to be far more surprising than anyone expected. In 2001, a geologist named Simon Wilde from Curtin University in Western Australia was working in a region called the Jack Hills, a remote, sun-baked stretch of ancient rock about 800 kilometres north of Perth. He was searching for zircons. Zircons are minerals, zirconium silicate to be precise. They form deep in magmatic rock. They are chemically almost inert, resistant to heat, pressure and chemical attack. And they incorporate uranium into their crystal structure at the moment of formation. Because uranium decays into lead at a known, constant rate, zircons function as atomic clocks. Measure the ratio of uranium to lead in a zircon crystal, and you can calculate its age with precision measured in millions of years. Wilde found a zircon grain in the Jack Hills that he dated at 4,400,000,000 years old. Earth itself formed 4,530,000,000 years ago. This zircon crystallized just 130 million years after the planet came into existence. In geological terms, that is essentially immediately. But the age was not the most important thing about this crystal. The most important thing was the oxygen isotope ratio locked inside it. Oxygen, like hydrogen, comes in multiple isotopic forms. The ratio of oxygen 18 to oxygen 16 in a mineral records the temperature and chemical environment in which the mineral formed. Zircons that crystallize from magma in the presence of liquid water at relatively low temperatures carry a distinctive oxygen isotope signature, a higher ratio of oxygen 18 than you would expect from purely high-temperature, dry crystallization. The Jack Hills zircon had that signature. The conclusion, published in Nature in 2001 and subsequently confirmed by multiple independent analyses, was that liquid water existed on Earth's surface 4,400,000,000 years ago, 130 million years after the planet formed. This was revolutionary. At the time, the dominant model of early Earth was something scientists called the Hadean Hell, a period of uninterrupted, globe-spanning magmatic chaos in which temperatures were far too high for liquid water to persist at the surface. The Jack Hills zircon demolished that picture. The early Earth had cooled far faster than the models suggested. Water was present almost from the beginning. But this created a new puzzle. The late heavy bombardment, the storm of asteroids that is the primary candidate for delivering carbonaceous chondrite water, did not occur until approximately 4 billion years ago, roughly 400 million years after the Jack Hills zircon formed. So some water must have arrived earlier. The leading explanation involves a process called magmatic degassing. When the early Earth was assembled from colliding planetesimals, some of those planetesimals already contained water, locked into hydrated minerals, carried inward from the outer solar system by the very gravitational dynamics we have already described. As the planet melted and the magmatic ocean churned, that water was gradually released from the rock, outgassed in the technical term, and rose toward the surface. Some escaped to space, stripped away by solar radiation. But some accumulated. Some condensed as the surface temperature dropped. A 2005 analysis by Professor Hidenori Genda of the Tokyo Institute of Technology estimated that magmatic degassing could have supplied between 3 and 8% of Earth's current ocean volume. Small in absolute terms, but enough to explain the liquid water suggested by the Jack Hill's zircon. So the timeline looks something like this.
In the first 100 million years of Earth's existence, a thin veneer of water begins to accumulate, drawn partly from the hydrated minerals in the rocks that built the planet, and partly from the constant drizzle of smaller impactors carrying water-rich material from the outer belt. Temperatures are dropping. The magmatic ocean is solidifying. Water is collecting in low points on the surface. Then, beginning perhaps 4,200,000,000 years ago, and accelerating sharply around 4 billion years ago, the late heavy bombardment begins. The storm of carbonaceous asteroids that Jupiter scattered inward during the Grand Tack period is now being further destabilized by the orbital resonance between Jupiter and Saturn. The volume of water-rich material arriving at Earth increases dramatically. But there is a brutal paradox at the heart of this delivery system. The same impacts that are delivering water are also destroying it. A carbonaceous asteroid 5 kilometers across, striking the early Earth at perhaps 20 kilometers per second, releases energy measured in sextillions of joules. The impact vaporizes rock, throws debris into orbit, and sends a shockwave through the mantle. It also vaporizes any surface water for thousands of kilometers in every direction. The early ocean, such as it was probably destroyed and rebuilt multiple times. Professor Nadia Drabon of Harvard University published an analysis in 2021 examining geochemical signatures in some of Earth's oldest surviving rocks, looking for evidence of this cycle of destruction and reconstitution. What she found suggested that major impacts during the late heavy bombardment did indeed evaporate the surface ocean repeatedly, returning Earth to a state of superheated steam atmosphere. But after each evaporation event, the water condensed again, sometimes in thousands of years, sometimes in millions. And each time it accumulated slightly more material from the ongoing rain of asteroids. The ocean was being built in layers, one catastrophe at a time. By approximately 3,800,000,000 years ago, the bombardment had tapered enough that the ocean could persist continuously. The temperature stabilized. Chemistry began its slow, improbable march toward biology. And roughly 3,500,000,000 years ago, in shallow tidal pools, in hydrothermal systems on the ocean floor, in films of water clinging to the surfaces of coastal rocks, something that was not quite life yet crossed a threshold and became something that was. All of that, every step of that chain, required water. Specifically, it required the kind of water that could only have arrived via the particular sequence of planetary events we have just traced. Different isotope ratio, different story. Different Jupiter orbit, different water budget. Different timing on the late heavy bombardment, and the ocean never stabilizes long enough for chemistry to take hold. Which brings us to the part of this story that has nothing to do with the past. In August 2018, the Italian instrument MARSIS, aboard the European Space Agency's Mars Express spacecraft, sent radio pulses through the southern polar ice cap of Mars and analysed the reflections. One particular reflection, coming from a depth of 1.5 kilometers below the ice, had a characteristic that should not have been there. It was consistent with liquid water. A subglacial lake. Approximately 20 kilometers across, likely hypersaline, the salt content prevents freezing even at sub-zero temperatures, hidden under 1.5 kilometers of ancient ice on a planet we thought was completely dry. This was not an isolated discovery. It was the beginning of a catalogue. Europa, the moon of Jupiter, roughly the size of Earth's moon, has been known since the 1990s to possess a subsurface ocean. The evidence: a magnetic field signature that changes as the moon orbits through Jupiter's own magnetic field, indicating a conducting fluid beneath the surface and a surface of fractured ice that shows every sign of being underlain by liquid, is now considered definitive. The volume of Europa's ocean is estimated at somewhere between 2 and 3 times the total volume of all Earth's oceans combined. A moon a fraction of Earth's size, containing more liquid water than our entire planet. Enceladus, the small moon of Saturn with a diameter of only 500 kilometers, erupts. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, flew directly through the plumes of material jetting from cracks near Enceladus's south pole and tasted their chemistry. It found water vapor, molecular hydrogen, organic compounds, silica nanoparticles that could only have formed in hot, mineral-rich water at high pressure. These are precisely the chemical signatures of hydrothermal activity, the kind of chemistry that, on Earth, supports entire ecosystems at the bottom of the ocean in the complete absence of sunlight. Ganymede, the largest moon in the solar system, has a subsurface ocean. Callisto, another moon of Jupiter, almost certainly has one. Titan, the remarkable moon of Saturn with its thick nitrogen atmosphere and lakes of liquid methane, may have a water ocean buried beneath its frozen crust. Even Pluto, 4.5 billion miles from the Sun, with surface temperatures approaching -230 degrees Celsius, shows evidence from the New Horizons flyby of 2015 of a subsurface ocean that may still be liquid today, kept from freezing by the radioactive decay of elements in its rocky core. The pattern is unmistakable. Water is not a peculiarity of Earth. Water is the solar system's most abundant liquid. It exists in ice or liquid form on dozens of worlds. It forms spontaneously wherever hydrogen and oxygen meet at the right temperatures. It is not the exception. It is the rule. And beyond our solar system, the evidence is equally compelling. The Hubble Space Telescope detected water vapor in the atmosphere of the exoplanet K2-18b in 2019. In 2023, the James Webb Space Telescope confirmed the detection and added carbon dioxide and methane to the chemical inventory, a combination that, on Earth, is invariably associated with biological processes. Water, it turns out, is a universal solvent, not just chemically, but cosmologically. It appears to be the default state of matter in a universe dominated by hydrogen and oxygen, which makes the question of Earth's oceans subtly different from the question it first appeared to be.
The question was never really whether water could exist here. Water was always going to find its way to rocky planets in habitable zones. The question was whether the particular chain of events in our solar system, Jupiter's migration, the grand tack, the late heavy bombardment, the specific isotopic composition of carbonaceous chondrites, assembled those water molecules into something stable enough and sustained enough to allow life to begin. A 2023 study from the University of Copenhagen analysed water from a range of sources: deep ocean drill cores, Antarctic ice nearly 3 million years old, modern rainfall, ancient fluid inclusions in mineral crystals, looking for subtle isotopic heterogeneity that might preserve a record of multiple delivery sources. What they found was consistent with at least 3 chemically distinct components in Earth's water inventory. One matches the isotopic signature of carbonaceous chondrites. One matches the signature of solar wind synthesized water. A third, smaller component appears to reflect an even older source, possibly interstellar water ice from the molecular cloud that predated the solar system itself. Let that sit for a moment. Some of the water in Earth's oceans may predate the Sun. It may have been present as ice in the interstellar cloud that collapsed to form our solar system 4.5 billion years ago. It survived the formation of the Sun, the violence of the early solar system, the late heavy bombardment, the complete and repeated vaporization of the early ocean, 3.5 billion years of geology and biology, and it ended up in the glass on your table. Water does not give up, which is perhaps why, wherever scientists look for it in the universe, they find it. And it is why, when the James Webb Space Telescope turns its infrared eyes toward the disks of gas and dust surrounding young stars in nearby stellar nurseries, the places where new solar systems are forming right now, it finds water ice, abundant, ubiquitous, already present in the building material before the first planetesimal has formed. The solar system you live in is not unusual in having water. What may be unusual is the particular combination of factors: the mass of the planet, the presence of a large stabilizing moon, the distance from the star, the chemistry of the impacting bodies, the orbital history of a nearby gas giant, that allowed that water to remain on the surface long enough to do something extraordinary with it. And we are left with a conclusion that is, on reflection, both humbling and strangely moving. The water in that glass did not come from Earth. It came to Earth. It was assembled from hydrogen forged in the Big Bang 13.8 billion years ago, and oxygen cooked in the cores of massive stars that lived and died before our sun was born. Those atoms drifted through interstellar space, collided and bonded into ice on the surface of dust grains, survived the formation of the solar system, hitched a ride on asteroids that Jupiter hurled inward across hundreds of millions of kilometers, survived impacts of almost incomprehensible violence, condensed and evaporated, and condensed again over hundreds of millions of years, and eventually settled into the stable, warm, oxygen-rich ocean that covered most of this planet when the first living cell divided. That water has flowed through every ocean that has ever existed on this planet. It has been lifted into clouds and fallen as rain,
and carved canyons and filled glaciers and evaporated into the atmosphere of a world that was almost unrecognizable compared to the one we inhabit. It has passed through the bodies of every creature that has ever lived on Earth. Every bacterium, every trilobite, every fern, every dinosaur, every early human ancestor who cupped their hands in a stream and drank. You are not just made of water. You are made of water that has a 4.5 billion year history of surviving everything the solar system could throw at it. Now go back to the beginning, back to the question we started with. Where did Earth's water come from? The honest answer, the answer supported by isotope ratios and spacecraft data and computer simulations and zircon crystals from the Australian outback, is that it came from everywhere. From the outer asteroid belt, delivered by carbonaceous chondrites whose water had been sitting in the dark beyond the snowline since before the planets existed. From the surfaces of dust grains, where the solar wind synthesized it atom by atom over millions of years. From the rocks of the planet itself, which sweated it out as they cooled. And perhaps, in some small fraction, from the interstellar cloud that existed before the sun ignited. All of those sources contributed, in different proportions, at different times, through a sequence of events governed by the orbital mechanics of gas giants, the physics of isotope fractionation, and the simple, ancient chemistry of 2 hydrogen atoms and 1 oxygen atom, finding each other in the dark. It is not a tidy story. Science rarely is. But it is, when you look at it whole, something very close to a magnificent one. The glass of water you picked up at the beginning of this hour is 4.5 billion years old. It is older than the moon. It is older than the oceans. It has been waiting, in one form or another, since before the Earth existed. Waiting for a planet cool enough, large enough, and lucky enough to hold it. You are that luck, looking at itself. Pick up a glass of water, any glass. Look at it. That water is not from Earth. By every law of physics, Earth should be as dry as Mercury. When our planet was forming 4.5 billion years ago, the temperature at its surface was high enough to vaporize any water into space. Permanently. And yet oceans exist. Rivers run. You are 70% water, which means it came from somewhere else. But from exactly where? That is one of the most fiercely contested questions in modern science. Because every time scientists think they have found the answer, new data turns everything upside down. This is the story of the greatest detective investigation in the history of this planet, and the clues are scattered across the entire solar system. If you are interested in how science solves mysteries that seem impossible, please subscribe to this channel. Your support genuinely helps us keep making this work. Thank you. September 28th, 1969. A Sunday morning in the small Australian town of Murchison. Population 800 people. Most of them are heading to church. At 10:58 in the morning, the sky tears open. A fireball screams across the atmosphere from northwest to southeast. The sound, a rolling, bone-deep concussion, is heard 500 kilometers away.
Fragments begin raining down on the town. One punches through the roof of a barn. Another lands in the middle of a road. Local farmers run outside and find dark, fist-sized stones with a strange glassy crust, as if they had been partially melted and then flash frozen in an instant. And then there is the smell. One farmer picks up a fragment and later describes the odour as something like methylated spirits. Organic. Chemical. Wrong, somehow, for a rock that just fell from the sky. Within days, scientists from across Australia are descending on Murchison. The stones are collected, catalogued, shipped to laboratories on 3 continents. And what those laboratories find over the following years will permanently change the way we understand where Earth's water came from. But to understand why that meteorite mattered so profoundly, we first need to understand the problem it was helping to solve. A problem that begins not on Earth, but in the catastrophic, violent infancy of the solar system itself. Imagine the Sun at roughly 2 million years old. That is an infant by stellar standards, a furious, unstable infant. Around it spins an enormous, flat disk of gas and dust, the raw material from which all the planets will eventually form. The inner region of that disk, close to the young star, is brutally hot. Temperatures near what will become Earth's orbit reach several thousand degrees Celsius. At those temperatures, volatile compounds, water, carbon dioxide, ammonia, cannot exist as solids. They are vaporized instantly and pushed outward by the relentless pressure of what scientists call the T-Tauri wind. The T-Tauri wind is what very young stars do before they settle down. They blast their surroundings with a torrent of charged particles hundreds of times more intense than the solar wind we experience today. This wind acts like a colossal pressure hose aimed at the inner solar system, stripping away anything light enough to be carried off. Water is light enough. The boundary where temperatures drop enough for water ice to survive as a solid is called the snow line. In our early solar system, that boundary sat at roughly 2.5 astronomical units from the Sun, just beyond where Mars would eventually form, right at the inner edge of what we now call the asteroid belt. Inside that line, in the zone where Earth was assembling itself from colliding rocks and dust, water simply could not persist. The numbers are unforgiving. The surface temperature of early Earth during the magmatic ocean phase, when the entire planet was essentially a globe of molten rock, exceeded 1,200 degrees Celsius. Water boils at 100 degrees. At 1,200, the molecule itself tears apart. Hydrogen escapes to space. Oxygen bonds with iron and silicates in the rock. There is no mechanism by which liquid water survives those conditions. And if you want a real-world demonstration of what happens to a rocky planet that cannot hold on to its water, look no further than Mars. Mars sits farther from the Sun than Earth. It is colder. It formed closer to the snow line. By every reasonable expectation, it should have retained more water than Earth, not less. And 4 billion years ago, it did. The evidence is carved into its geology. Ancient river valleys etched into the southern highlands, the ghost of an enormous ocean basin in the northern lowlands, minerals that only form in the sustained presence of liquid water. Mars once had oceans. Shallow, perhaps, brief, perhaps, but real. Then it lost them. Its smaller mass meant weaker gravity. Weaker gravity meant a thinner atmosphere. A thinner atmosphere meant less protection from solar radiation. Over roughly the first billion years of its existence, the water evaporated, the hydrogen bled off to space, and Mars became the desiccated wasteland that every Mars rover has crossed in silence. Earth faced the same starting conditions. Earth did not end up the same way. The question that has occupied planetary scientists for decades is precisely this: why not? The answer begins with chemistry, specifically with one of the most powerful analytical tools in all of modern science, a technique called isotope analysis. Once you understand how it works, you will understand why it transformed the search for Earth's water from speculation into something approaching a genuine forensic investigation. Hydrogen, the H in H2O, is not a single uniform thing. It exists in nature in two stable forms. Ordinary hydrogen has a nucleus containing just one proton. But there is a heavier version called deuterium, whose nucleus contains one proton and one neutron. That extra neutron makes deuterium roughly twice as heavy as ordinary hydrogen. When deuterium bonds with oxygen to form water, the result is what chemists call heavy water. Chemically identical to regular water in most respects, but measurably denser and detectable with precision instruments. The ratio of deuterium to ordinary hydrogen in any sample of water, scientists write it as the D to H ratio, functions like a chemical fingerprint. Water that formed in the cold, radiation-rich environment of interstellar space tends to be enriched in deuterium. Water that formed closer to a warm star, where radiation breaks deuterium bonds more readily, tends to be depleted in it. The specific D to H ratio of Earth's oceans is a fixed, well-measured value. Approximately 1 deuterium atom for every 5,100 ordinary hydrogen atoms. That number is the key to the entire investigation. Find a source, an asteroid, a comet, a cloud of interstellar gas, whose water carries that same ratio, and you have found the origin of our oceans. The hunt was on, and it led first back to that dark, foul-smelling rock that fell on Murchison, Australia. The Murchison meteorite belongs to a class called carbonaceous chondrites, specifically the CM2 subtype. These are among the most ancient solid objects in the solar system. They formed 4,500,000,000 years ago, before Earth itself existed, from the same primordial disk of dust and gas. They have barely changed since. They are, in effect, preserved samples of the raw material the solar system was built from, frozen in time, carrying the chemical memory of the earliest solar system in their mineral structure. When scientists cracked open the Murchison fragments and analysed what was inside, they found something that stopped the laboratory cold. Water. Not traces, not hints. Real, chemically bound water locked into the crystal lattice of hydrated silicate minerals. The kind of water that does not evaporate at room temperature because it is not sitting freely. It is woven into the atomic structure of the rock itself. Roughly 12% of the Murchison meteorite's total mass was water. And when researchers measured the D to H ratio of that water, they found it sitting tantalizingly close to Earth's oceanic value. Not identical, close. Frustratingly, provocatively close. By the 1990s, systematic isotope analysis of multiple carbonaceous chondrite types, Ci chondrites, Cm chondrites, Cr chondrites, consistently showed their water falling in a range that bracketed Earth's measured value. The chemical fingerprint was beginning to align. But the obvious objection was immediate. Yes, these meteorites contain water with the right isotopic signature.
But how many of them fell on early Earth? In what quantities? The question is not whether individual rocks carry water. The question is whether enough of them arrived in sufficient total mass to account for 1,380,000,000 cubic kilometers of ocean. That volume resists easy comprehension. Here is one way to approach it. If you could drain every ocean on Earth and refill them using a pipe delivering water at the rate of 1 cubic kilometer per second, a flow rate that dwarfs every river on Earth combined, it would still take you 43,000 years to finish. That is the volume of water we are trying to explain. Where did all of it come from? The answer arrived not from a chemistry laboratory, but from the surface of the Moon. When the Apollo missions returned lunar samples between 1969 and 1972, geologists began noticing something strange about the distribution of craters on the lunar surface. The density was not uniform. Some ancient highland regions were so saturated with overlapping craters that the surface looked like the face of someone who had survived every possible catastrophe simultaneously. Other regions, the dark, smooth maria, were geologically recent and relatively unmarked. When radioisotope dating established precise ages for rocks from the heavily cratered zones, a pattern emerged that no existing model had predicted. The overwhelming majority of the Moon's largest impact craters formed within a remarkably narrow window of geological time, approximately 4 billion years ago, plus or minus perhaps 100 million years. This concentrated, sudden pulse of bombardment was given a name: the Late Heavy Bombardment. And it was not a local lunar event. The same signature appears in the ancient geology of Mars, of Mercury, and, though the evidence is harder to read on a geologically active planet that constantly resurfaces itself, almost certainly of Earth as well. Something had destabilized the solar system approximately 4 billion years ago, long after the initial chaos of planetary formation had subsided, and sent a renewed storm of asteroid-scale objects raining down on the inner planets. The total mass of material estimated to have struck Earth during this period ranges from 10 to 20 quintillion kilograms. If a meaningful fraction of those impactors were carbonaceous chondrites, water-rich rocks from beyond the snowline, the arithmetic of ocean formation begins to work. But this raised the most important question in the entire investigation. What disturbed the asteroid belt so dramatically 400 million years after the solar system had apparently settled into stability? The answer to that question involves the largest planet in the solar system, and understanding what Jupiter did to the early solar system will transform this story into something genuinely unexpected. In 2005, a team of planetary scientists working at the Observatoire de la Côte d'Azur in Nice, France, published a paper that became one of the most cited and debated works in planetary science of the past 2 decades. The lead author was Alessandro Morbidelli, The computational model they described has been known ever since as the Nice model, after the city where it was developed. The Nice model set out to answer a deceptively straightforward question. Why do the four giant planets, Jupiter, Saturn, Uranus, Neptune, occupy the orbits they hold today? The answer, the team argued, is that those are not the orbits they were born in. They migrated dramatically, irreversibly. In the earliest phase of the solar system, Morbidelli's model proposed the four gas giants were packed into a much more compact configuration, orbiting between roughly 5 and 15 astronomical units from the Sun. Beyond them stretched an enormous disk of smaller bodies, the primordial material that would eventually evolve into the Kuiper Belt. For several 100 million years, the system maintained an uneasy equilibrium. Then Jupiter and Saturn drifted into a gravitational resonance. Their orbital periods synchronized into a precise ratio of 1 to 2. Jupiter completing exactly 2 full orbits for every single orbit completed by Saturn. That resonance acted like a structural frequency matched to the natural vibration of the system. The entire outer solar system destabilized. Uranus and Neptune were thrown onto new, much wider orbits. They ploughed through the outer disk of small bodies like freight trains through a crowd. Thousands of those objects were flung inward toward the Sun, toward the inner planets. That was the late heavy bombardment. But 6 years later, Morbidelli and colleagues published an extension of the Nice model that addressed an even earlier period. And this is where the story of Earth's water becomes genuinely extraordinary. This extended model is called the Grand Tack hypothesis, and it proposes something that, when you first encounter it, sounds almost too dramatic to be real. Jupiter, in the first few million years of the solar system's existence, before the inner planets had even finished forming, migrated inward from its birthplace near 5 astronomical units all the way down to approximately 1.5 astronomical units from the Sun, almost to where Mars sits today. It came within striking distance of the inner solar system. And then it stopped, turned around, and migrated back outward. The reversal was caused by Saturn. As Jupiter moved inward through the disk of gas and dust, Saturn, still forming in the outer regions, was pulled into its own gravitational resonance with Jupiter. The combined interaction generated a net outward force that arrested Jupiter's inward drift and dragged it back toward its current position. The maneuver resembles, in orbital mechanics terms, the sailing maneuver called a tack, turning a vessel into the wind and back out again. Hence the name. The consequences of this migration for Earth's water were profound. As Jupiter swept inward through the region between roughly 3 and 5 astronomical units, the zone straddling and just outside the snow line, it acted as a gravitational plough on an astronomical scale. It scattered the water-poor, rocky bodies of the inner belt region inward toward the Sun, and simultaneously it captured water-rich carbonaceous bodies from farther out, asteroids that had formed beyond the snow line laden with ice and hydrated minerals, and deposited many of them into what would become the main asteroid belt. Jupiter physically relocated water-rich material from the cold outer solar system and parked it in a zone from which it could eventually rain down on the inner planets. Without that migration, the asteroid belt would contain a fraction of the carbonaceous chondrites it holds today. Current planetary formation simulations suggest that removing Jupiter's grand tack from the calculation reduces the total water delivered to early Earth by at least an order of magnitude. 10 times less water. Possibly no stable ocean. Possibly no life. Jupiter did not merely shield Earth from asteroid impacts over geological time, which is the role popular accounts usually assign to it. Jupiter built the delivery system that supplied Earth's oceans. Without the grand tack, this planet looks like Mars. Now, in 2023, the most precise confirmation of the asteroid hypothesis arrived in a sample capsule the size of a cooking pot, falling through the Australian sky on a parachute. The spacecraft was Hayabusa 2, built by the Japan Aerospace Exploration Agency. It launched in December 2014, travelled 300 million kilometres to a small, dark, diamond-shaped asteroid called Ryugu, a C-type carbonaceous body chemically related to the carbonaceous chondrites that isotope analysis had identified as the primary candidates for Earth's water source. Hayabusa 2 spent 18 months in orbit around Ryugu, descended twice to collect surface and subsurface samples, and returned those samples to Earth in December 2020. When the analysis of Ryugu material was published in 2023, the result was as close to a definitive answer as planetary science has ever produced. The D to H ratio of water extracted from Ryugu samples, 1 to 157 micromolar. Earth's oceanic value, 1 to 156 micromolar. 1 unit of difference, within the margin of measurement error. A match so precise it leaves almost no room for alternative interpretation. The chemical fingerprint lifted from the asteroid matched the fingerprint in Earth's oceans. After decades of investigation, the primary source of Earth's water had been identified with a confidence that approaches certainty. But science, when it is working properly, never stops at the most comfortable answer. And in 2021, a team at the University of Glasgow published a paper in Nature Astronomy that introduced a third source of Earth's water, one that had been invisible to researchers for the simple reason that nobody had thought to look for it in the right place. Professor Luke Daly and his colleagues were studying microscopic dust grains collected from the surface of a different asteroid, Itokawa, by the original Hayabusa mission in 2010. They used a technique called atom probe tomography, an instrument capable of analysing the composition of matter one atom at a time, to examine the outermost surface layer of those grains. We are talking about a depth of a few nanometers, a layer thinner than a soap bubble, thinner than the wavelength of visible light. In that vanishingly thin surface layer, they found water. Not ancient water locked into mineral structure over billions of years. Freshly synthesized water created by the solar wind. The mechanism is this. The solar wind is a continuous stream of charged particles flowing outward from the sun at hundreds of kilometers per second. The vast majority of those particles are protons, bare hydrogen nuclei. When those protons strike the surface of a silicate mineral, which is rich in oxygen,
They embed themselves into the crystal lattice and react. Hydrogen plus oxygen equals water. The reaction happens atom by atom across the entire sunlit surface of every asteroid, every dust grain, every rocky body in the inner solar system, continuously, for billions of years. The water produced this way carries a very different isotopic signature from the water in carbonaceous chondrites. It is almost completely free of deuterium. Its D to H ratio is far below Earth's oceanic value. And here is where the two sources fit together with an elegance that is almost architectural. Carbonaceous chondrite water is slightly too enriched in deuterium relative to Earth's oceans. Solar wind synthesized water is dramatically too depleted in deuterium. Mix them in the right proportion, and the result is precisely Earth's oceanic value. One source too heavy, one source too light. Combined, the exact measurement we find in every ocean, river, glacier, and raindrop on this planet. A portion of Earth's water, estimates suggest somewhere between a few percent and perhaps somewhat more of the total, was not delivered from the outer solar system at all. It was manufactured, molecule by molecule, on the surfaces of the dust grains and rocky bodies that were already part of Earth's building material. The sun, in a real chemical sense, helped water its own planet. Which leaves one final question in the timeline. When did the first ocean actually form? And the answer to that arrived from a place as remote and sun-scorched as anywhere on Earth. Western Australia, the Jack Hills region, 2001. Geologist Simon Wilde of Curtin University was searching these ancient red rocks for zircons. Zirconium silicate crystals, chemically inert, resistant to temperatures exceeding 1,800 degrees Celsius, virtually indestructible over geological time. They incorporate uranium into their crystal structure at the moment of formation, and because uranium decays into lead at a precisely known rate, each zircon functions as an atomic clock. Measure the uranium to lead ratio and you can read the age of the crystal to within a few million years. Wilde found a zircon grain and dated it 4,400,000,000 years old. Earth formed 4,530,000,000 years ago. This crystal solidified just 130 million years after the planet came into existence. In geological terms, that is essentially the first moment the crust was cool enough to form solid rock. But the age was secondary to what the oxygen isotope ratio inside the crystal revealed. Oxygen, like hydrogen, exists in multiple isotopic forms. The ratio of oxygen 18 to oxygen 16 in a mineral records the temperature and chemical conditions in which the mineral crystallized. Zircons that form from magma in the presence of liquid water at relatively low temperatures carry a distinctive signature, an elevated ratio of oxygen 18 compared to what you would expect from purely high-temperature, dry crystallization. The Jack Hill zircon had that signature. The conclusion, published in Nature in 2001 and confirmed by multiple independent analyses in the years since, was unambiguous. Liquid water existed on Earth's surface 4,400,000,000 years ago, 130 million years after the planet formed. This demolished the then dominant model of early Earth as an uninterrupted hellscape of molten rock and superheated atmosphere, a world far too hot for any surface water to persist.
The Jack Hill's zircon showed that Earth cooled faster than the models predicted. Water appeared almost immediately. But this created a new puzzle. The late heavy bombardment, the primary delivery event for carbonaceous chondrite water, did not occur until approximately 4 billion years ago, some 400 million years after the Jack Hill's zircon formed. Something must have delivered water earlier. The answer involves a process called magmatic degassing. When Earth assembled itself from colliding planetesimals in the first tens of millions of years of its existence, some of those planetesimals already contained water, locked into hydrated minerals carried inward from the outer solar system by Jupiter's gravitational influence, operating even in those earliest phases. As the magmatic ocean churned at temperatures exceeding 1,000 degrees, that water was gradually cooked out of the rock, rising through the molten material toward the surface like steam rising through a pot. Much of it escaped to space, stripped away by the T-Tauri wind of the young sun. But some accumulated. Some condensed as the surface temperature began to drop. Some pooled in low points on the cooling crust. Analysis by Professor Hidenori Genda of the Tokyo Institute of Technology, published in 2005, estimated that magmatic degassing alone could supply between 3 and 8% of Earth's current ocean volume, enough to explain the liquid water recorded in the Jack Hill's zircon, enough to seed the first shallow seas before the main asteroid delivery had even begun. So the full timeline emerges. In the first 100 million years, a thin veneer of water appears, drawn from the hydrated minerals in Earth's building blocks and from the continuous low-level rain of smaller impactors. The surface cools. The crust solidifies. Water collects in the first basins. Then, beginning perhaps 4,200,000,000 years ago and intensifying sharply around 4 billion years ago, the late heavy bombardment arrives. The carbonaceous asteroids scattered inward by Jupiter's grand tack are now being further destabilized by the orbital resonance between Jupiter and Saturn. The delivery of water-rich material accelerates dramatically. But there is a brutal paradox embedded in this timeline. The same impacts that are delivering water are simultaneously destroying it. A carbonaceous asteroid 5 kilometers across, striking at 20 kilometers per second, releases energy measured in sextillions of joules. It vaporizes rock. It throws debris into orbit. It sends shock waves through the mantle, and it vaporizes any surface water within thousands of kilometers of the impact site. The early ocean was not built once. It was built and destroyed and rebuilt repeatedly over hundreds of millions of years. Professor Nadia Drabon of Harvard University, publishing in 2021, examined geochemical signatures in some of Earth's oldest surviving rock sequences, looking for evidence of this cycle. What she found was consistent with major impacts during the late heavy bombardment repeatedly evaporating the surface ocean, returning Earth to a state of superheated steam atmosphere before the water condensed again, sometimes over thousands of years, sometimes over millions. Each time the ocean reformed, it incorporated additional water from the continuing asteroid rain. Each cycle left the planet slightly more hydrated than before. The ocean was assembled in layers, one catastrophe at a time. The last major impact large enough to completely vaporize the global ocean
occurred approximately 3,800,000,000 years ago. After that, the bombardment tapered. The ocean stabilized. The temperature settled into a range compatible with sustained chemistry. And, roughly 3,500,000,000 years ago, in conditions that scientists are still working to fully reconstruct, in hydrothermal systems on the ocean floor, in tidal pools at the edges of ancient volcanic islands, in thin films of water clinging to mineral surfaces, chemistry crossed a threshold. Something that was not life became something that was. Every step of that chain required water, not just any water. Water with a specific isotopic composition, delivered in specific quantities through a specific sequence of planetary events that required Jupiter to be the size it is, to have migrated the way it did, to have parked water-rich asteroids in exactly the right reservoir at exactly the right time. And now we arrive at the part of this story that extends beyond the past. In August 2018, the Italian radar instrument MARSIS, aboard the European Space Agency's Mars Express spacecraft, sent radio pulses down through the southern polar ice cap of Mars and analyzed the returning echoes. One reflection, from a depth of 1.5 kilometers below the ice surface, carried a characteristic that the team's lead researcher, Professor Roberto Orose of the Bologna Institute of Radio Astronomy, initially doubted when he saw it. It was consistent with liquid water. A subglacial lake approximately 20 kilometers across, kept liquid by dissolved salts that depress the freezing point even at the temperatures found deep beneath Martian ice. Mars, the planet we had written off as completely dry, was hiding an ocean underground. This was not an isolated discovery. In the decade since Cassini completed its mission at Saturn in 2017, the inventory of water in the outer solar system has expanded in ways that continue to redefine what is normal for a planetary system. Europa, the moon of Jupiter, possesses a subsurface ocean whose volume is estimated at between 2 and 3 times the combined volume of all Earth's oceans. A moon smaller than Earth's moon, containing more liquid water than our entire planet, kept liquid by the tidal heating generated as Jupiter's gravity flexes the moon's interior with every orbit. Enceladus, Saturn's small moon with a diameter of just 500 kilometers, erupts. The Cassini spacecraft flew directly through its southern polar plumes and detected water vapor, molecular hydrogen, organic compounds, and silica nanoparticles that could only have formed in hot, mineral-rich water at high pressure, the precise chemical signature of hydrothermal activity on the moon's ocean floor. On Enceladus, the same chemistry that may have given rise to life on Earth is happening right now, in an ocean buried beneath ice, heated by the same tidal forces that warm Europa. Ganymede, the largest moon in the solar system, has a subsurface ocean. Callisto almost certainly has one. Titan may have a water ocean beneath its frozen crust, in addition to the lakes of liquid methane that make its surface resemble a cold, hydrocarbon version of early Earth. Even Pluto, 4.5 billion miles from the Sun, with surface temperatures approaching negative 230 degrees Celsius, likely conceals a liquid water ocean beneath kilometers of nitrogen ice, kept from freezing by the slow decay of radioactive elements in its rocky core. The pattern is impossible to ignore. Water is not a peculiarity of Earth. Water is the default state of chemistry in a solar system built from hydrogen and oxygen, the first and third most abundant elements in the universe.
It forms wherever the temperature and pressure are right, on rocky bodies and icy moons, and in the atmospheres of gas giants, in conditions ranging from the warmth of Europa's ocean floor to the frozen dark beneath Pluto's surface. And beyond our solar system, the James Webb Space Telescope has begun reading the atmospheres of worlds orbiting other stars. In 2023, Webb's infrared instruments detected carbon dioxide, methane, and what appears to be dimethyl sulfide in the atmosphere of the exoplanet K2-18b, a world roughly 8 times Earth's mass, orbiting in the habitable zone of its star. On Earth, dimethyl sulfide is produced almost exclusively by living marine organisms. The detection is not confirmed as biological, but it is the first time a molecule with a plausible biological source has been identified in the atmosphere of a potentially habitable world beyond our solar system. Water, it turns out, is a cosmic inevitability. It appears to be synthesized wherever hydrogen meets oxygen under the right conditions, in interstellar molecular clouds, in the disks of gas surrounding newly forming stars, on the surfaces of asteroids bombarded by solar wind, in the subsurface oceans of moons orbiting gas giants hundreds of millions of miles from the nearest star. What is not inevitable, what required a specific and improbable sequence of events, is what happened to the water once it arrived on Earth. The right distance from the star. A planet massive enough to hold an atmosphere against solar radiation, but not so massive that it became a gas giant. A large moon to stabilize the axial tilt and prevent the wild climate swings that would otherwise make the surface uninhabitable on geological timescales. A gas giant neighbor large enough to have scattered water-rich material inward at the right moment in history. A late heavy bombardment intense enough to deliver the bulk of the ocean, but not so intense that it sterilized the planet permanently. And a long, slow tapering of that bombardment, giving chemistry enough uninterrupted time to stumble toward self-replication. Change any one of those parameters significantly, and the story ends differently. Change Jupiter's mass by a factor of 2, and its migration history changes, and the asteroid belt chemistry changes, and the water budget changes. Move Earth 10% closer to the Sun, and the water evaporates. Move it 10% farther, and it freezes. Give Earth half the mass, and the atmosphere bleeds off. Take away the Moon, and the axial tilt processes chaotically, driving climate swings too rapid for life to track. We exist in a narrow corridor, and water is what that corridor is paved with. A 2023 study from the University of Copenhagen analysed water from sources spanning 3 billion years of Earth history. Deep ocean drill cores, Antarctic ice nearly 3 million years old, fluid inclusions trapped in ancient mineral crystals,
and found isotopic heterogeneity consistent with at least 3 chemically distinct source components. One matches carbonaceous chondrites. One matches solar wind synthesized water. A third, smaller component appears to predate the solar system itself. Interstellar water ice from the molecular cloud that collapsed to form the Sun and planets 4.5 billion years ago. Some of the water in Earth's oceans may be older than the Sun. It survived the formation of the star. It survived the violence of planetary accretion. It survived the late heavy bombardment. It survived the complete and repeated evaporation of the early ocean. It survived 3.5 billion years of geology, plate tectonics, volcanic eruptions, mass extinctions, and the slow transformation of the atmosphere from methane to oxygen to nitrogen. And it ended up in the glass on your table. Now come back to the beginning. Back to the question we opened with. Where did Earth's water come from? The answer that 4.5 billion years of planetary history and 50 years of scientific investigation has assembled is this. From everywhere. From the cold outer reaches of the asteroid belt, where carbonaceous chondrites had been sitting since before the planets existed, loaded with water that Jupiter scattered inward during its grand tack migration. From the surfaces of dust grains and small rocky bodies, where the solar wind built water molecules one atom at a time across billions of years of continuous bombardment. From the planet's own rocks, sweated out during the magmatic ocean phase as the first crust cooled. And from interstellar space itself. Water ice that predates the Sun, carried in the dust that seeded the solar nebula before the star ignited. Not one source, not two, all of them. In the right proportions, at the right times, on the one planet in this solar system that was positioned and sized and accompanied by the right gravitational neighbours to hold on to what arrived. The detective investigation is not entirely closed. The precise proportions of each source are still being refined. The mechanism by which the early ocean survived the heaviest phases of bombardment is still being debated. The data from Ryugu continues to generate new publications every few months as the analysis deepens. Science, when the question is deep enough, never fully stops. But here is what we know. Here is what the isotopes and the spacecraft and the zircons and the simulations all point to, with a coherence that grows stronger every year. The water in that glass did not originate on this planet. It assembled over billions of years from hydrogen forged in the Big Bang 13.8 billion years ago, and oxygen cooked in the cores of massive stars that lived and exploded before our sun was born. Those atoms drifted through interstellar space, bonded into ice on dust grains in the cold molecular cloud that would become our solar system, survived the formation of the Sun, rode inside asteroids that Jupiter delivered to the inner solar system, survived impacts of almost incomprehensible violence on the surface of a young planet, evaporated and condensed and evaporated again through hundreds of millions of years of bombardment, and finally settled into the stable, sunlit ocean that covered most of this world when the first cell divided in the dark.
That water has flowed through every ocean this planet has ever possessed. It has been lifted into clouds and fallen as rain, and carved canyons and built glaciers, and dissolved minerals and carried nutrients from mountains to sea floors. It has passed through the body of every living thing that has ever existed on Earth. Every bacterium, every trilobite, every fern, every predator that stalked the Carboniferous forests, every dinosaur that drank from a Cretaceous river, every ancestor of yours who ever cupped their hands at a spring and drank. You are not merely made of water. You are made of water that has spent 4.5 billion years surviving everything the solar system could throw at it, and arriving, against considerable odds, here. Pick up that glass again. It is not just water. It is the record of a journey longer than anything else you will ever hold in your hand. And somewhere in that journey, in the precise chemical accident of the right isotope ratio, the right asteroid composition, the right planetary neighbour, the right distance from the right star, is the reason you are here to hold it at all.